We're going to use the diagram of this strip of magnesium metal and going to express the isotopes and the relative abundance. So let's count. All right, let's see what isotopes we have. Okay, got a 26 there, so magnesium 26. How many of them do we see? 1, 2, there's another one there, and that's it. There's 2 of them. 2 out of how many? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so 2 out of 20. That's 10%. What else do we got? Magnesium 24. And how many of them do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 out of 20. And magnesium 25 is 1 and 2. So those are our 3 isotopes, and there's 2 of them. Then we should add up to 20. We do. Yeah, 2. All right, the relative abundance, we can punch that in our calculator. This is going to be 10%. This is going to be reduced out to 8 out of 10, right? 8 out of 10 is 80%. Yep. And this is also 10%. Oh, let me get back to my colors. Right, and then that's 10%. All right, let's see what else we got. Consider the natural abundance given to us here. Is the sample illustrated? I'm reading down here. Is the sample illustrated in the strip of magnesium accurate in the representation of the at the atomic level? All right, so is it accurate? Relative abundance is 80. We said this was 80%. That's pretty good. Pretty close considering there's only 20 atoms that it showed us. And the rest were 10%. So yeah, yes, reasonably accurate. Explain, because it matches the data. What else is there to explain? So yes. Right, it matches the data. Pretty close. 80 is close to 79, and 10 is close to 10, and 10 is close to 11. All right, number 3. If you could pick a single atom of magnesium, and here, I'm reading here. If you could pick up a single atom of magnesium and put it on a balance, what would the mass of that atom most likely be in AMU? What's going to be, this is probability, since you have more magnesium 24s than any other isotope, you are most likely to pick up magnesium 24, because you have an 80% chance of doing that and 10% chance of picking up the other in our sample. Below are Jack and Allen's methods for obtaining average atomic mass, which is a weighted average. So whose method was correct? All right, well, Jack's method is correct because he's using the weighted average approach. In other words, he's taken into consideration the percent or the relative abundance. So there's your 10%, there's your 80%, there's your 11%, and so he's factoring in the relative abundance, and this number should be the number or very close to the one on the periodic table. Whereas Allen is not considering the relative percent. He's just taking the 3 isotopes and dividing it by 3. Now that would be okay if there were equal amounts of each isotope, but there isn't. There's clearly more of the isotope magnesium 24, so he didn't consider that. That was it.